Hello, my name is Eric Johnson, and welcome to Serverless Streams, Messaging, and APIs. This is a tech talk on serverless technologies. And so we're going to get started. I'm glad you've joined us today. So a little bit about me. Who am I? This is me. I'm not pretty. I'm funny. That's my job. I'm EDJ Geek if you follow me on Twitter or if you'd like to. I am a senior developer advocate for serverless at AWS. I'm a geek about serverless tooling and automation. I'm a dad of 5, and no, that's not a typo. My wife is a superhero. I'm a husband of 1. That's superhero. And I'm a musician. A drummer. Some of you may not say that's a musician, but I believe it is. So these are my loves and these are my life. But one of my favorite things to talk about is serverless. And so we're going to jump in and start doing that today. And I hope this proves helpful to you. So why are we here today? Well, we're going to talk about serverless and patterns that help you do serverless right. But first of all, let's define serverless. You know, when you put 100 people in a room and you say, what is serverless, you'll get probably 105 answers because you'll get 5 people that go, yeah, I want to change my answer after they hear the rest. But what is serverless? The way we define serverless here is several things. First of all, no infrastructure provisioning or management. That's one of the things that we see key in serverless is that you don't have to take care of the infrastructure to run your application. Second thing is automatic scaling. You need your application to scale, and scaling is up and down. So when you think about elasticity of your application, as you need more infrastructure, it scales up to match that load, and as your load drops, it scales down, so you're not paying for something you don't use. You pay for value. So going again back to this cost thing, you only pay for what you use. So on a Lambda, we'll talk about pricing later on in this conference, but on a Lambda or serverless technologies, again, you only pay for what you use. So when you invoke a Lambda, you pay for it. Other than that, it's not being charged. Finally, highly available and secure. So Amazon takes on that part of the relationship in that we build an infrastructure that's going to be highly available. It's going to be, multi redundant. So, you can different availability zones, and it's going to be secure. So that's how your infrastructure is going to be underneath. So when you think about a serverless application, it really is a pretty simple idea. First of all, you have an event source, and that can be changes in data state, request to endpoints, changes in resource state. When that event happens, it's going to trigger a function. And that function can have any number of languages. We've only listed a few of them here, but you could have Node, Python, Java, C#, Go, Ruby, Rust via the custom runtime. In fact, what we have is last year at reInvent, we announced what's called a custom runtime where you're able to create your own language. We've seen PowerShell, we've seen COBOL, we've seen Rust, we've seen Elixir, all kinds of different things. So when that function is triggered, it then acts upon a service. And really, the services can be anything. It can be a database, it can be your cloud, it can be something outside, inside. It's kind of up to your own imagination on what you can do with your function. So when we're talking serverless, it's really this kind of event source and function that we're going to be looking at today really kind of heavily. So when you think of common Lambda use cases, there's several. First of all, one of the most common we see is web or mobile backend, where a very common practice is to have like a client on the front end, and we use API gateway, and then behind that will be Lambda, DynamoDB, Aurora Serverless, something like that. Second thing is we see a lot of file processing. And these aren't in particular order, they're just some of the more common ones. We see a lot of file processing. What that means is if you drop a file into an S3 bucket, something's going to happen. So you'll drop an image into an S3 bucket, and then that will get modified, blown up or scaled down, optimized, black and white, something like that. We also see a lot of queue processing. And as we get into the patterns, we'll dig into this more. But the idea here is I can use an SQS, and I can queue up events, and then I can trigger those using a Lambda, do some kind of work based on this queue. Amazon Kinesis, real-time stream processing. And really what this means is, so Amazon Kinesis allows a lot of data to come in at one time. It's a highly scalable ingestion pattern. And so as you pull data in, you can use Lambdas to do real-time stream processing. You can actually connect to the stream and modify and look at data and do analytics and different things like that. Notification processing. So this is the pub sub of serverless. So you publish to a topic, and then other things may subscribe, like a Lambda can subscribe to that topic. And so when you publish to that topic, that Lambda is triggered. See that a lot. And then scheduled jobs. And I can't see you, but virtually raise your hand if you have a cron server up and running. Very common pattern when we do operations is to have some type of server that just, and maybe it's in it's somebody's desk but somebody has a computer that runs cron jobs. And one of the cool things about Lambda and using CloudWatch is you can do time-based events out of CloudWatch. So you can say, hey, every 5 minutes trigger this Lambda, and then that will take the cron jobs out of there. So what you're not doing anymore is you're not running a computer to do that, and you're not paying for the time for this computer. Because while I was joking about being on someone's desk, when you run them in the cloud, it could be like a T2 instance or something like that, which may not cost a lot, but it's more than you have to pay, when really you could handle it through just triggering a Lambda. So as we go into this, when we talk about patterns, one of the first things we need to understand is the microservice and understanding exactly what a microservice is. So a real basic example is something like this. This is a basic serverless API-based microservice. And the idea here is that you have an API gateway, like we talked about earlier, and it's going to be in front of a Lambda, and then that Lambda is going to interact with DynamoDB. And so your client will call Amazon API Gateway, and there you have it. Now, a lot of times when we want to build this up, and this is a very simple application, but we want to build this up and we get more into enterprise level, and we need it to do more. And our first instinct is we'll just add more logic to this Lambda. But the reality of that is, instead of adding more logic to the same Lambda, we want to split this out and just add another Lambda. And so what we're looking at doing here is as you build out more functionality and have the need for more functionality, don't put it in the same Lambda. You can move it out to another. And this is the idea of microservices. And so what you're doing is that Lambda has one job, and it does that job really well. So it's a single responsibility. And then the next Lambda does another job and does really well. And they can each have their own table. Although with DynamoDB, we do recommend, when you look at DynamoDB architecture, a lot can be done with a single table as well. So both Lambdas can interface with one table, or you can split those out. When you look at the microservices iceberg, though, one of the common questions we get is, should every service of mine talk to another using an API? Do I need an API for everything? Well, really, maybe not. Most microservices are internal only. For a given product support their customer-facing features, they may only need to pass messages to each other that are simple events and not need a full-fledged interaction API. And so what that means is we have this one point for people to access our service, but underneath that, we may be doing a lot that doesn't need to be an API call. So what we're going to do is focus on the stuff below the water. Instead of the public interface, we want to look at what do the internal services look like. All right, so when we're looking at this, we're going to talk about microservice patterns, and this is really going to be a lot of the meat of what we're talking today, and how do we attack these microservice patterns. So one thing to understand is the Lambda execution model. As we climb into this, you need to understand how Lambda can be executed and the different ways of doing that. There's three basic ways. The first is synchronous, or you might call it a push pattern. So what that means, and a great example of this is like Amazon API Gateway. What you're going to do is you're going to have a client, much like we talked about. It's going to make a request to Amazon API Gateway, and then Amazon API Gateway is going to either proxy or integrate with Lambda, and you have an endpoint, and that's it. So the synchronous part of this is, let's say you have your client's going to make this call, and it expects a response back. Now, we're not talking, a lot of times we talk about, synchronous, maybe look at our client, but, or asynchronous at our client, but what we're talking about is the overall pattern here is I make a request, I get a response, okay? The second execution model is an asynchronous or event-based. And this is, we get a lot of power of this, and this is not somewhere people often go first, but it's something that I challenge you to look at and say, hey, maybe I can do this asynchronously and not keep my customer waiting. And this is going to come through on something like an Amazon SNS, where we'll push to the topic and then we move on. So our client will push to the topic and they don't have to wait for an answer. They just know something's going to happen in the back end. Another example is Amazon S3, and this goes back to our earlier example where we're dropping images into a bucket and then we want something done. We don't want to make our clients sit there and wait and spin and spin and spin while that work's being done. Instead, we want them to move on and then we'll notify them later that it's done. So in this asynchronous event, the Amazon SNS, the Amazon S3, and many other services will make a request to Lambda function after the fact. The third pattern we have is stream or pull-based. And this is where you're going to look at things like Amazon DynamoDB or Amazon Kinesis. And if you didn't know, I mean, we talked about Kinesis earlier and how it in itself is a stream, but if you didn't know, DynamoDB also has a stream, and it's kind of like on the backside of Dynamo. As you make changes to DynamoDB, it's going to log changes to the stream, and then you can react from that stream. You can read the stream and make changes. So great way to do things after the fact. Look, we've got our data into the database. Now we can react to that. We'll climb into that a little bit later. The way this works is the Amazon AWS Lambda service actually does some work here for you in that it's going to pull for the changes and then trigger the function as needed. And you can set batch size on these and different things. So again, those are our three patterns, either synchronous or push, asynchronous or event, and stream or pull based. So one thing to understand here is the kind of the basic synchronous call would be the Lambda API itself. So Lambda has an API on it that you can invoke directly. It's provided by the Lambda service. It's used by all other services that invoke Lambda. So what that means is when you invoke an API, it's actually going to then, or an API gateway, it's actually then going to invoke the Lambda service through the API to get the data. You can also invoke that through your SDK. Let's say you on a Lambda, you wanted to trigger another Lambda, something I don't suggest necessarily because, we try not to couple up our applications, but you can if you need to. Or even from a client side, if you have permissions, you can do it from a browser. Again, maybe not something I would suggest for security, but possible. But this kind of synchronous invocation can be done, and it's part of all the SDKs. And you can pass the event payload structure you want, and you have a lot of control there. So when we look at other patterns and how they work, we talk about SNS plus Lambda and exactly how it works. And kind of give you an idea. It's simple, flexible, fully managed, pub sub. And if you're not familiar with pub sub, a lot of developers will talk about this. Yeah, we use pub sub. Put it on the queue, put it on the topic, put it on whatever. And queue actually isn't part of pub sub, but you get the idea when we talk about this idea of being able to pass messages around. And so in PubSub, what we do is we create a topic. And when you have that data, we push to that topic. We say, all right, here's the data. And we don't have to wait for a response because the way SNS is built is we know we're going to trust that it's reliable and it's going to do its job. And we don't have to wait for that response. When we push data to that SNS topic, then what's going to happen is 1, 2, 5, or 30 Lambdas can get triggered, or something else. The cool thing about SNS is you can have any number of subscribers and any type of subscribers. Okay, so it can be a Lambda, it can be an HTTP endpoint, it can be an SMS message. There's a lot of different things that can be done. So a lot of power going on here. And the cool thing is you can let's say I push some data. I don't want everything to trigger based on this. So I don't want to send an SMS message if it's something that should trigger Lambda. So I can use messaging filters to make sure it's only sent to certain subscribers. And this is an asynchronous type call like we talked about before. The next pattern we're going to look at is Amazon SQS plus Lambda. So SQS plus Lambda, again, a little different. So here, what you're going to have is you're going to have a message queue. Okay, so that's going to when the message goes into SQS, rather than broadcasting like SNS did. Okay, so when we pushed a message into SNS, we broadcast it out to those subscribers. In this respect, these are going to pull the SQS to look for data. So what happens is a message is inserted into the queue. Number 2, the Lambda function is invoked. And number 3, SQS removes messages from queue on successful response from the function. Okay, so what happens here is it used to be up until about 6 months ago, you would pull that or it would handle for you, and then you would have to tell SQS, hey, this worked, delete it from the queue. But now with Lambda, what we've done is if you return a 200, then it removes all the batch items that were part of that batch. Okay, so let's say you have a batch limit of 10. So your Lambda is going to get 10 messages one time. If all of those are successful, then it tells SQS to remove them. Now, if one of them fails, then they're all put back in, okay? So that's important to know. So when you're writing your application, it's important to understand that your event might get triggered more than once. And so your data needs to be able to handle that. Application needs to be able to handle that. Idempotent is the word that I struggle to say, but that's how it needs to be configured. So the next pattern we're going to look at is Amazon Kinesis streams plus Lambda. Okay, with this pattern, data, and again, this is usually massive amounts of data. SQS can handle a lot. Kinesis can handle a whole lot, and it handles it through sharding. So as you need more, you can create more shards in the stream, and there's a certain amount of bandwidth, egress or ingress and egress, and we'll talk about that down the road here in just a minute. So what this does the data is published to the stream. It can be any kind of producer. The Kinesis returns stream data. The Lambda pulls the stream, and the Kinesis returns stream data. Okay, the Kinesis, the Lambda itself kind of handles the ordering, because one of the things about Kinesis is it needs to be in order. With SQS, you can get out of order, and it'll just, if you have one fail, they'll move on. With Kinesis, it's going to keep it in order. So if you have something that continues to fail, it'll actually act as a blocker until that's fixed, so that you make sure that your data is still in order. So again, Lambda receives batches and potentially batches of batches, so you can get a lot of data coming through. The other cool thing here is at reInvent last year, we announced something called consumers. And when we're talking about bandwidth on a Kinesis, you're able to connect to a 2 megabyte egress pipe, for lack of a better word, and any Lambdas connecting that share that amount. Okay, and that's one way of doing it, and that works fine. But if you need to have more egress, if you need to have, you can add up to what are called 5 consumers. Each one of those has a 2 megabyte egress on them per shard per second. Okay, so you're able to spread that out, and then each consumer can handle 1 Lambda. So you can connect to up to 5 Lambdas, and each one gets 2 megabyte per shard per second egress. And that does cost a little more, but if you really need to be doing 5 different things with that data in real time, it's something to look at. If you don't need to do the 5 and you can and just keeping it down to 2 or 3, then the normal polling will work just fine, the standard process. So the other pattern we're going to look at, this is the last pattern at the moment, is step functions. Step functions are a very powerful tool. One example where here a while back, I was working with somebody, and we built a Lambda to handle strike payments. And in building out we were doing subscriptions and all that. So I had a lot of if-thens, and I'm not going to lie, my Lambda logic did not look great. And what I realized later is I could do this through step functions. Step functions makes it easy to coordinate components of distributed applications. Each of these green boxes and the clear box can be a Lambda or some other service. And so step functions handles the orchestration and it handles erroring. So rather than you having to write a bunch of erroring into your Lambda, if the Lambda fails, the step function can then do something else. So for instance, you have the failure capture here. You can also run parallel tasks. A lot of power to step functions. If you're doing orchestrated workflows, I highly suggest you look at this. Again, very powerful. So how do you compare the services? When we're talking about, how do I make the choices? And so I want to give you some information that'll help you kind of figure that out. And there's 6 ways that we can we can compare them. The first is scale and concurrency controls. The second is durability. The third, persistence, consumption models, retries, and pricing. All important things and all things to think about. Now, before we climb into this, I would tell you that as you're trying to make decisions, think about what's important to you. Is durability important? And most of the time you would say yes, but there are some people who go, you know what, it's okay if I lose a little data because it's not that important. Now, that's not very common, but you may say, you know, durability is crazy important to me, or persistence is important. You know, I need stateful type things. You know, again, a lot of things to think about on this. So the first thing, like I said, we're going to look at is scaling and concurrency controls. And what we're going to do is kind of talk through the different ones and how they work. When you think of Lambda API, you have to think of concurrency as a point in time. It's not total per second, but a point in time. Okay, and so that means generally you have 1,000. So what it is, you have 1,000 requests per second across all your functions in a region. That's a soft limit. You can request an increase on that, but that's the default. Okay, and so you got to think about how many instant requests am I getting at a time. And by default, no per function concurrency throttle is set. So again, it's across all functions, but you do have the ability to go in and set a per function concurrency. And that's, you may ask yourself, you know, why would I do that? I don't need to limit this. Well, while Lambda may scale to your load, behind or downstream Lambda, it may not. So to protect downstream, you may add some concurrency control on this to that particular Lambda. For SNS, the service automatically scales, and you use Lambda per function concurrency setting to control downstream consumption. So again, this goes back to if I'm triggering a Lambda from SNS, I can use that Lambda per function concurrency to protect downstream. SQS also, the service automatically scales. Use Lambda trigger batch size settings and per function concurrency settings to control downstream consumption. So if you know your downstream can't handle more than maybe 10 per second, you can set that concurrency. Or maybe, you know, it's not so much, I just want to control the load maybe through the batch. So you can kind of turn those two knobs to see, you know, what's going to work well for you. Finally, with Kinesis streams, and again, this goes back to, you know, I was saying we would talk about the how fast, or the ingress and the egress. So the way Kinesis streams work is there are shards in the stream, and one shard provides an ingest capability of 1 megabyte per second or 1,000 records per second, and it has up to 2 megabytes per second of data output or egress. So you've got a lot of speed coming in, and again, you can add shards. So, you know, I mean, the math is simple. If you do 5 shards, then you get 5 megabytes per second and 5,000 records per second, and 10 megabytes per second per shard per second of data output. So pretty straightforward there. So let's talk about the Lambda per function concurrency controls. So concurrency is a shared pool by default, like we talked about. You could separate that using the per function, and it acts as a reservation. Okay, it also acts as a max concurrency per function. So it's especially critical for data sources like RDS, where, you know, we want to control how much we're pounding it, and how much, you know, we're hitting that service. So and it also acts as a kill switch. And we've had people say, look, you know, if something's wrong or something, you know, my Lambda's not firing right, I need to stop it. So you can set that per function concurrency to a 0, and that'll actually be the kill switch for the Lambda. So looking at concurrency across models, they're handled slightly different. So with SNS, an API, or the SNS API, there's no event store, right? So you're not actually saving, you know, at Amazon API Gateway or at the SNS, you're not saving these events, right? They just trigger the Lambda. However, built into SNS is a retry. Okay, so and we'll talk about that in a minute, but there is some controls written in that said, hey, if this doesn't work, then I want you to retry it, and there's a pattern for that. So for queue-based concurrency models, it builds up in a queue. So it builds up in a queue, and then it triggers a Lambda, and again, you can set batch size on how many you want to hit the Lambda with at one time. And again, like we talked about earlier, if they all succeed, then it clears from the queue. If they don't, then they're put back into the queue. And it's the idea behind, just to kind of make it clear, when a batch is sent to a Lambda, it's hidden in the queue, so they're not sent to another Lambda. However, if it fails, then they reappear in the queue, and your order will get messed up if there's some failures, and it kind of gets messed around. So something to be aware of. There is such a thing called a FIFO queue, which is a first in, first out, that'll help you with the order as well. For stream-based, so what you've got is just massive amounts of data coming in on the different shards, and each shard. So if I connect one Lambda to a shard, then if I have 5 shards, then effectively I'm triggering 5 Lambdas. They're all doing the same thing off that data from the shard, but the Lambda does scale with the shard. So as you scale up, the Lambda scales up to handle that as well. So let's look at concurrency versus latency and how these work. So when you think about a stream, something to understand, the maximum theoretical throughput is the number of shards times 2 megabytes per second, right? That's our egress. But the effective theoretical throughput is different, okay? Because what happens is if you have functions that are failing or that are taking too long or have to go into retries, that affects your throughput, right? So you're looking at the number of shards times the batch size divided by, the function durations, retries. The math goes beyond me, really, honestly. And so what you want to understand is, if your put ingestion rate is greater than theoretical throughput, you want to consider increasing the number of shards, but you also want to look at make sure your Lambdas are working and make sure they're working properly. Is your timeout long enough? Are you properly handling promises? Are you properly handling code? Try catch, different things like that. Because as your Lambdas fail, it hugely affects the throughput on your streams. For everything else, the maximum processing rate is the maximum concurrency divided by the average duration, so your events per second. And the effective processing rate is effective concurrency over your average duration. So again, how those affect, you can talk theoretical, but effective is what's important. You use You can use concurrency metric and duration metric to estimate processing time. So monitor that stuff and see what's happening, because you'll be able to say, hey, I think that's taking too long. Let's take a look at that. So the next thing we're going to talk about is durability. For durability, each of them are handled different ways. So with Lambda API, the Lambda API is built to be highly available but offers no durability requests. What this means is if it fails, it's not going to keep your data. You need to handle the retries, okay? Because generally it's in your code, okay? With SNS provides durable storage of all messages that it receives. And upon receiving a publish request, SNS stores multiple copies. Okay, so when you store that, it's going to duplicate it out, all right? And so today, and it's got across multiple availability zones. So if we did have a disruption in availability zone, it would probably be unnoticed to your clients because you've got data copied out. Excuse me. With SQS, again, same thing. Stores all message queues and messages within a single highly available AWS region in multiple redundant availability zones. Okay, so there's no single computer, network, or AZ failure that can make the messages inaccessible. And finally, Amazon Kinesis synchronously replicates data across 3 availability zones. Are you seeing a pattern here? Really, honestly, the takeaway or the short version is data is replicated across multiple availability zones for all 3 of these services. That's SNS, SQS, and data streams. So your data is going to be durable. Persistence. Lambda API has no formal persistence model, and don't be tricked into that. All right, do follow that. We've heard some people say, well, but if it's warm, it's possible your stuff might be there. No, there's no persistence model in Lambda API. So you want to make sure that you're doing stateless applications there, or that your persistence is stored somewhere else. With SNS, there's no formal persistence model beyond delivery retry logic that extends up through potentially 13 hours. SQS, by default, messages are stored for 4 days, so you have a good amount of time to work with that. This can be modified to as little as 60 seconds or up to 14 days. So if you have some things that are going to queue up and you need to really take it easy on your back end, you're able to do that. Kinesis streams. By default, the data is stored for 24 hours. You can increase this up to 168 hours, which is 7 days, and that extended data rate retention cost 0.02 per shard hour above 24 hours. So there's some cost to extending that data. All right, so when we talk consumption, so there's an invocation model and there's some guidance. When you think about Lambda API, it can be sync or async from client to a single invocation. We've talked about the different patterns that can happen. However, we really want to point out again that for complicated Lambda to Lambda workflows, use AWS step functions. Now, earlier you remember me saying don't invoke Lambda from Lambda, or it's probably not good practice, and it isn't. What you want to be able to do is you want to be able to have something guiding through that. Now, I'm not saying that because I think the Lambdas are going to crash. It's just not the way we build applications, right? We try to decouple our applications so that if one service dies in a microservice world, the other services aren't aware it can still go on and do their job. Well, if I couple two Lambdas together and one is reliant on the other, then I've got a problem. But if I'm putting a bunch together through step functions, then they're not aware of each other, and step functions is handling the orchestration. So again, strong model. If you have a lot of orchestration going on, use step functions. For SNS, the async to Lambda, SNS can fan out to multiple subscribing Lambda functions using the same message, which we talked about. Again, use the message filtering to control which messages go to which subscribers, and use message delivery status to track failures. For SQS, Lambda service pulls message from queue and invokes Lambda on your behalf, so you don't have to worry about the pulling. It'll do that for you. And it scales pulling based on in-flight messages. So what that means is as it's pulled, it's going to do a long pull, and then as it starts to get messages coming in, it speeds that up. Okay, and then as it reduces, it slows down a little bit. So you can call message delete from within your code, or let service handle it via successful Lambda function execution. I suggest the second. It's less code. Takes the burden off you. For Kinesis data streams, the Lambda service pulls messages from streams and invokes Lambda on your behalf. Like we talked about, it can run multiple applications to consume the same stream for different needs. Again, this goes back to that where they share it. So if you have multiple applications, so that means that they're doing, let's say, 3 different things. They can connect to the shard. If you get beyond that, you might want to look at using what we call the enhanced fan out, which is the consumers I was talking about earlier. You can use the AWS Kinesis client library. You can configure batch size so that your function has enough time to complete processing of records. So that's something to watch out for. Make sure that your batch size, if it's too big and you can't complete it and it times out, then we're back to that bottleneck we talked about earlier. So we've alluded to this several times, but let's kind of lock this down on the retry and failure handling. In the Lambda API, retry failure logic is client dependent for synchronous invocations. For asynchronous invocations, they're retried twice by the Lambda service. So let me explain what this means. What we're talking about is how you're invoking the Lambda, okay? So if you're doing synchronous, like through an API call and your client's calling that, if it fails, you need to write into your client code to make that change. But an asynchronous might be something like a story or SNS triggering it. And what happens is if it fails, then it's retried twice by the Lambda service. Okay, we'll talk about what happens after that if it goes beyond. In SNS, if a Lambda is not available, SNS will try 2 times, and so here's that pattern we talked about. Retry 2 times at 1 second apart, and then 10 times exponentially backing off from 1 second to 20 minutes, and finally 38 times every 20 minutes for a total of 50 attempts. And I'll let you work through the math on that, but it's over 13 hours before the message is discarded from SNS. For SQS, the messages remain in the queue until deleted. So they are prevented from being accessed by other consumers during the period of time known as the visibility timeout, which is what we talked about when you access something. There is a visibility timeout. Successful Lambda invocations will cause deletions of the message automatically. If an invocation fails or doesn't delete a message during the visibility timeout window, it is made available again for other consumers. Again, so if your application was successful and did write data, then you need to make sure that it can handle that. And Kinesis streams, when using the Kinesis client library, it maintains a checkpoint cursor of processed records and will retry records from the same shard in order until the cursor shows complete. And a lot of this also is handled with the Lambda service. If you connect through services or you connect Lambda directly through it, it'll handle that for you. All right, so we said, what happens, if it goes beyond and it's not working? Well, we have a thing called the dead letter queues, okay? By default, a failed Lambda function invoked asynchronously is retried twice, like we talked about, and then the event is discarded. Using a dead letter queue, you can indicate to Lambda that unprocessed events should be sent to an Amazon SQS queue or Amazon SNS topic instead. So what happens is if they fail, then hey, let's push this event out, and then we can do something with it, okay? I highly suggest you turn this on, okay? For async use cases, you want to be able to monitor, okay? So when you monitor this through the SQS queue length, that gives you some visuals into, hey, something's not working right. If my dead letter queue is building up, something's not working right, okay? And so I'm not necessarily losing that data. I may have to, maybe I just choose to process it manually later, or I can write in an automated function, okay? So if you use SNS, send a message to something durable and a trusted endpoint for processing. So again, you can send them back to something else, however you want to route that. And on this last thing, if and when things go boom, because they do, because everything breaks, DLQ can save your invocation event information. And again, this goes back to how important is my data. Most people would say very important, so we need that. And the last comparison is pricing. So with pricing, one thing to notice is that big yellow tag at the bottom. First 1 million requests are free per month. And it's on everything with the star. Okay, so it's the first three things. So on the Lambda API, per request, you pay 20 cents per request, 0.20. SNS is 0.50. And there's some things to look at that. For each 64 kilobyte chunk of delivered data is billed as one request. And there's no charge for deliveries to Lambda. Okay, so again, you're not charged for that. So SQS, again, per request, 40 cents. Each 64 kilobyte chunk of payload is billed as one request, much like SNS. And a single request can have from 1 to 10 messages. So again, when you're talking about your batch size, you might look at upgrading your batch size to not have to trigger that each time. And then Kinesis per shard hour and per request put payload. So you see shard per hour is 0.015 and put payload units 0.014. And then again, there's some factors of each 25 kilobyte chunk of a payload. Our build is one request. And then with the enhanced fan out, as I talked about earlier, and extended data retention can cost extra. Okay, so when you're going back to Lambda, I want to point out with the Lambda SNS and SQS, these are great for enterprise and down to startup, because when you think about when you're doing a startup, you're able to test Lambdas and you're able to do those 1 million requests, for free, practically free. We have companies that are running small to medium, even large applications that are efficient and well optimized for next to nothing, because they're taking advantage of the first 1 million requests are free per month. And unlike other free tier stuff, this is not for the first year. This is just part of the pricing model. All right, so we've talked through a lot of data and on how you can compare, but a lot of times I just have people say, look, just tell me what to do. So I'm a visual guy, so I want to show you some architectures that'll help you kind of make decisions and help you on how you think about building serverless applications. So the first thing we do is we look at fanning out, and this is a fan out improperly. So if we have an application that needs to write to two tables and then to a bucket and then needs to call Amazon recognition and then needs to call Amazon transcribe, and we do it with one Lambda, what we're looking at is a bunch of promises if you're a node, or a bunch of synchronous calls, or however you're going to do it. But it's a lot of calling services and a lot of waiting, which really we probably don't need our client to do, okay? So one of the answers to that I see is, okay, well, we'll do this. All right, so we'll call other Lambdas. Well, I'm kind of broken the rule that I was talking about earlier, where we generally, unless we have a good reason, we generally don't call other Lambdas. And if you think about this, this doesn't really get us anywhere. We're still in that first Lambda. We're still waiting for those other Lambdas to respond, okay? To fan out properly, we would use a topic, okay? So our client be it whatever, could be, it could be any number of things. What it does, it pushes a message to the topic. That topic is then pushed to all of the application or all of the Lambdas at one time. So instead of doing number 1, the number 2, the number 3, all 5 here are getting hit at the same time. And then later you can check for, hey, was that, you can pull from your client, you can have some type of trigger that messages, look at your cloud events, watch things like that to see, hey, make sure everything happened. Okay, so by using the simple notification service, that allows you to fan out properly. One of the other patterns I see a lot is bottlenecked patterns here. And what we got is we want to do something like Amazon recognition, but we need to, and Amazon recognition is very fast, but let's say you're just hammering it with events or pictures that you want to change. So we're taking a Lambda, we're doing that, and then we're dropping it in a bucket. Well, this is a pretty easy fix because what in reality we can do is we can put a queue in front of our Lambda. Okay, so that queue, and then we can do some batch sizing on that. Hey, only do 5 images at a time, or only do 2, or however we want to do that. And we can slow that down, and we don't overwhelm any of the services, and then it gets again, we get our data back and it's written to the bucket. So instead of bottlenecking, look at queuing for downstream. Okay, so in our last example, we're going to talk about thinking synchronously. Okay, a lot of times that's how people think. Okay, so again, synchronous versus asynchronous, and remember at the very beginning I said I challenge you to start thinking asynchronously. So in this example, we're going to take a phrase like, hey, how are you? And we're going to translate it. First thing we're going to do is translate it to maybe 5 different languages. Then once those are translated, we want each of those languages to be converted to audio. And we can do this first with Amazon Translate and then with Amazon Poly. Okay. Then we want to store those audio files. Okay. And then finally, we're going to take all the translations and the links to the audio files, and we're going to store them in a table. Okay, there's a good chance we may overwhelm this Lambda, or not overwhelm it because it's going to scale to as we need, but there's a good chance that this Lambda, we may not get our timeout set. It's going to take a while to do. Okay, so instead, one thing we can do is we can think asynchronously. Okay, so not one thing, this is the thing we want to do here. So if you think about this, we could actually submit our phrase and then store that phrase in a table, in a DynamoDB table. And if you remember, you go back, we had a DynamoDB table stream. We talked about the streams. Okay, as things are written to DynamoDB table, we can then read from the stream after the fact. So what we're going to do is we're going to store the phrase, and then we're going to trigger another Lambda that's going to do the translation of those, and then it's going to write that back to the DynamoDB table. Then what's going to happen is those are going to be added to the stream, and those are going to trigger a third Lambda to convert the audio phrases and drop them into the bucket. Okay, so all your client had to wait for was the phrase to be submitted, and then they moved on. Okay, so this allows us to think much more asynchronously. Okay, what can we do after the fact instead of having to wait and do it all right up front? It's a different way of thinking, and I challenge you to think about that as you're doing application, as you're building your applications. So a few things to think about in closing here. What you want to look at is what invocation resource is the right one for you. And some things to kind of ask is, how, for instance, real-time. How real-time is your real-time need? A lot of people will immediately say, I need real-time, it needs to be immediate, and that's nothing to it. But what we find out is maybe it can wait an hour, maybe it can wait 10 minutes. There's hot data, there's warm data, there's cold data, there's cool data. So you need to kind of figure out what works best for you. Does order matter? Should I be using a stream? Should I be using an SQS? Should I be using a FIFO SQS? Do multiple services need to feed off the same data? Again, should we use consumers? Do we need to fan out? Different things like that. What does breaking your Lambda function do what does breaking your Lambda function do to a bad code deploy have impact on? Okay, so this goes back to the calling one Lambda from another. Okay, if we break one Lambda and we've coupled them up like that, we're in trouble. So think about that, okay? And think about downstream. So think about what happens when a downstream service fails. Well, if we've got a queue in place, then our messages queue up and then resume when we get that fixed. If we don't, then we're losing data. So, and is there potentially a way to overwhelm a database or other services? So these are, again, things to think about on that. A couple more things. All of these services require a little care and feeding in terms of management. So you want to look at, what is it going to take to run this? What's it going to cost? Things like that. All are HIPAA eligible and PCI compliant. I want to take a pause there. One thing to understand, and I've had people say, so if I run Serverlessly and I put my application on your infrastructure, then I'm HIPAA compliant, right? Great. No, that's not true. Your infrastructure is HIPAA compliant and PCI compliant. Or I'm sorry, HIPAA eligible and PCI compliant. But your app still needs to be built that way. Okay, that's the shared responsibility model. We'll build the infrastructure that way, but the application is up to you to build to be HIPAA eligible and PCI compliant. I'll support fine-grained permissions with AWS IAM, so you can get really, really fine-grained on that. And again, they're all pay-as-you-go. So the FinAC there are many ways to get data between microservices. Again, Kinesis, SNS, SQS, there's a lot of patterns you can do. You might need an API that you create yourself. You might not. Think through the factor comparisons on scale, durability, persistence, the different comparing models that we looked at. And you'll probably end up needing more than one and potentially end up using each of these in some part of your infrastructure. Right tool for the job. That's really what it comes down to. I encourage you not to shoehorn a square peg in a round hole. Right tool for the job. Evaluate and test using CMCLI. You can do a lot locally, and you can test. And it's cheap to run in AWS too. If you're prototyping, it's going to cost you next to nothing. Serverless pricing models make testing new ideas low cost and easy to share or easy to get started with, much like I just said there. So, a couple websites I'm going to give you here. As we close out. The first is aws.amazon.com serverless to learn more about serverless. And the second is aws.amazon.com messaging to look through the different messaging services that we have. Again, SQS, SNS, Kinesis, and then there's others that we didn't touch on, which is MQ, Pinpoint, and the message broker, IoT message broker. With that, I thank you, and we are going to open it up to questions. First, I would encourage you with follow me on Twitter at EDJGeek. I often tweet about new services and things going on serverless, and sometimes about my kids, so, good with the bad. And now we're going to open it up to questions.